So good day, everyone. My name is Christian Sasser. I'm the astronomer in charge for iTelescope, and a very happy 2024. We've got a lot of interesting sessions, and we're starting off with Dr. Maggie Lieu, and she is a research fellow of machine learning and cosmology at the University of Nottingham in the Midlands, where I used to live. Can you believe it? Yes. And she's a very smart cookie, I can say. She has this incredible YouTube channel called Space Mog. Go and look at that. She's an excellent communicator. So, Maggie, yeah, come and join us. And you have to just switch your camera on. And there you are. Hello, how are you in the Midlands?
Hi, I'm good. How are you?
I'm very well. We're so excited to have you share all your experiences on cosmology, of course. It's going to be very interesting. And you're such a brilliant communicator. I've just told everyone about SpaceMog, but I'm sure you're going to mention that too to us. So without further ado, go ahead, share your screen, and I'll be quiet now. Thank you. And when you want to run the poll, by the way, just give me, just let me know, and I'll launch them. Thank you.
Can you see my screen, hopefully?
Yes, we can see it.
Yeah.
It's all good.
Perfect. My talk is on bending light to unveil the shadows, to explore the mysteries of like the biggest unknowns in our universe, like dark matter. I'm Dr. Maggie Lieu. I work at the University of Nottingham. I'm sure Christian has said. I'm an astrophysicist, but I also do machine learning there. And I run a YouTube channel called Space Mog, where I cover everything from space, astronomy, physics, and machine learning. I'm going to start my talk to tell you that the Earth is great. It's wonderful. There's so much to do here. There's everything is colorful and everything is wonderful. But there's a big problem, and that is that everything that we see and interact with around us only makes up 5% of the visible universe. That's like everything, even like the CERN, the stars, the galaxies, like anything we see through telescopes, or even in like X-rays and UV wavelengths that we can't see with our visible eyes, but we can see with detectors. This only makes up 5% of the universe. So maybe Christian can start. Was that the first poll that? So yeah, we've got a question there for you. What do you think makes up most of the universe?
Okay, what do you think?
It's a good like selection, isn't it? One person thinks ordinary matter, even though I pretty much said that 5% of the universe is ordinary matter that we see around us. But pretty good. Shall we take a look? Have a look. So ordinary matter is what we call baryonic matter. So it's made up of baryons, and 5% of the universe is baryons. About 27% is dark matter, and about 68% is dark energy. So we stick the word dark in front of it because we pretty much, we're not sure what it is really. The numbers here are like approximate. Various probes have been and experiments have been done to try and constrain the actual values of these, and I'll tell you a little bit later why that is so important. But dark matter, that's the thing that I'm most interested in, and this is like the focus point of this particular talk. So I'll ask Christian to start the second poll, if that's okay.
Yes, of course. Which one is it? What do you think dark matter is? That one?
Yeah,
Okay.
pretty good. A little bit of everything. The answer is actually nobody quite knows, and all of these things could be equally valid, right? So it might be ordinary matter. Some people think that it could be black holes or some of the kind of ordinary matter that we're just not seeing. It could be like planets or other normal matter, but when we're just not detecting it because it's so faint. It could be a completely different kind of matter and doesn't interact with light or it doesn't interact with normal matter or very weakly interacts with it. These are what we call weakly interacting massive particles, I guess. Some theoretical physicists, well, quite a lot of theoretical physicists actually, are working on new theoretical concepts to explain away dark matter. Maybe our current gravity theories are completely wrong and we need something else to explain it. So those who said I'm not sure were probably good, because us astrophysicists and physicists are not sure either, to be honest. Great. So dark matter. Let's see. So the concept of dark matter goes back to 1933, and it was like a Swiss Bulgarian astronomer known as Fritz Zwicky, who was looking at a cluster of galaxies, the Coma cluster of galaxies. So a cluster of galaxies is essentially galaxies that orbit around one another, just like how our planets orbit around the sun, how stars orbit around the center of our galaxy. Galaxies themselves will orbit around one another, orbiting in like a gravitational potential well, right? And so he was looking at this cluster of galaxies, and he realized that the galaxies were moving way too quickly. There wasn't enough gravity in the starlight alone to keep them bound together. They should be flying off in all directions because they're moving too quickly. And so he termed this dunkel materie, which is what we modernly know as dark matter today, or refer to as dark matter today. But it wasn't until the late 1960s, so like 50, 60 years ago, like half a century ago, that dark matter actually got popularized, and it was popularized by a lady named Vera Rubin. She essentially did the same thing, but in the context of a single galaxy. So she was looking at stars in a galaxy, and she was measuring their velocities. And she found that they were moving way too quickly. They should be flying off. And so you can make this plot, which is essentially speed on the y-axis and distance from the center of the galaxy on the x-axis. And what you expect to see from the starlight is that dashed line there, right? So it should go up and then down, because at the mass in the stars, velocity or speed goes, well, velocity squared goes as mass, right? So as you go further away from the galaxy, there's less light, which means there's less stars, which means that you expect the velocity to taper down. But instead, they see like this velocity getting higher and higher, and it doesn't seem to like drop down. So this is one of our best evidence for dark matter. And today we have been searching for this dark matter particle endlessly with many detectors and experiments here on Earth. And a famous example is the CERN experiment in France and Switzerland. Essentially, what they do is they smash particles together to at incredible speeds, trying to create new particles. And they found all sorts of new particles, quarks, etc. in these experiments. They found the Higgs boson, which gives particles their masses. But they've never been able to come up with something that is consistent with dark matter. And to give you an idea of like where we are with this is the latest results that I could find from the Atlas experiments, so one of these particle accelerators in CERN. And it looks very, very technical, but I'll walk you through it because it's not as complex as it seems. On the y-axis, we have the cross-section of dark matter. So if dark matter is a particle, the cross-section tells us how likely it is to interact with normal matter. And you can see it's similarly as like the area of a particle, right? So a larger area, if you had two particles, they're more likely to collide together, right? And if you've got a smaller area, then you're less likely to collide. That's essentially what the y-axis shows. And the x-axis is showing you dark matter mass, so how much mass such a dark matter particle has. Each of these lines in this plot is a different dark matter experiment. So you've got things like Panda, Lux, and Xenon, which are very famous dark matter detection experiments. And everything that's shaded, the red, the blue, the yellow, etc., these are areas where we've ruled out. So we've looked in this region of space, this cross section and this mass, and we haven't found any signs of dark matter. And these particle physicists, essentially, they're just using higher and higher energies to try and rule out more and more sensitivities to the cross section and to like smaller and smaller masses. And eventually they'll run out of space to search for. So hopefully we will find something within that remaining white space there. But if we go there and we don't find anything, then maybe our gravity theories are completely wrong and we need something else. So we haven't detected dark matter, and my talk is about how we can see dark matter. How can we do this? Well, thanks to Einstein, actually. So I'm sure he needs no introduction. Einstein in 1905 came up with his theory of general relativity, and it's a theory of gravity, essentially. He explained gravity not as a force, but in terms of how space-time, which is essentially like the fabric of the universe, interacts, reacts to matter. His theory actually can be simplified to this very simple equation here. And it's always incredible to me how you can explain so much with just a few like variables. So again, it looks kind of complex, but it's really, really simple. On the left-hand side, G mu nu, this is a curvature term. So this tells you the curvature of space-time. And it says it's equal to the 8 pi g. The g is a gravitational constant. So it's like gravity, essentially, divided by c to the power 4. C is the speed of light. Quite often, actually, you'll see c be defined as 1. And so you just get the 8 pi g term. And that's just some arbitrary constant that you set. And then T mu nu is the mass energy. Remember, E equals mc squared. So mass and energy are essentially equivalent. So basically what the theory of relativity tells us is that space-time tells matter how to move and matter tells space-time how to curve. Okay. And in practice, this is what you can see it as. Like this grid here reflects like a fabric of space-time. And you see any mass, a galaxy, the Earth, the sun, will kind of act to curve space-time, just like how if you put a massive object into a stretched piece of fabric, it will make it bend down. And that's how we saw it, right? And the thing with the theory of relativity is that any light traveling in this space-time, we know that light always takes the quickest path. And so the light won't travel in a straight line. It will kind of curve, follow the curvature of space-time. And I like to see this as if you've ever played with like one of those like penny machines where you put the penny in and there's like a big like dip thing, right? And you put it in and it just circles around instead of going straight. I see it in a very similar situation, and that's how Einstein was able to explain how planets orbit our sun as well, because it follows the curvature created by our sun. Now, in practice, if the Earth was, if the gravity of Earth was strong enough, this means that any light could be essentially bent by gravity. It wouldn't follow a straight line. Instead, it follows a curved line. This is what we know as gravitational lensing. Now, I told you that Einstein came up with his theory in 1905, but actually it wasn't until 1919 that we were able to kind of popularize this theory. And it came when Sir Arthur Eddington, he came up with an idea. And the idea was that, well, the Earth, its gravity isn't strong enough to bend light. But what else do we have in our kind of what else do we have to play with that has enough gravity, has a massive mass that could bend light? The obvious answer would be the sun. Except there's one problem. The sun is really bright, so even if it could bend light, we wouldn't be able to see it until 1919, when there was a solar eclipse. And what happened was that they took an exhibition to go and see this solar eclipse happen. So a solar eclipse is when the moon moves in front of the sun, blocks it out the light, and then you can see the stars behind the sun. And if Einstein was correct, then these stars would be deflected, their light would be like distorted, moved by the gravity of the sun. And indeed, that was the case. The amount that they moved was exactly what Einstein predicted in his theory of relativity. And overnight, Einstein became a big star. Now, the sun is a massive object, but in our universe, there's loads more massive objects. And the ones that I'm interested in are these things, clusters of galaxies. And this goes back to Fritz Zwicky and his original measurements of dark matter, Dunkelmaterie. This is an image from the Euclid Space Telescope taken recently, and it's the Perseid cluster of galaxies. And so in the concept of clusters of galaxies, again, the mass here is being shown. The mass here is the galaxy cluster. And the background light that we're interested in is from galaxies that are behind the galaxy cluster. And as the light from these faraway galaxies move within the vicinity of the gravity of a galaxy cluster, it will become bent around it. And the amount of distortion is dependent on the mass of a galaxy cluster. Thankfully for us, galaxy clusters are mostly dark matter. Actually, 90% of a galaxy cluster's mass comes from dark matter. And that's how we can see dark matter, essentially. I'll do this one more slide, and then I'll ask the last question, I think, Christian. So this is an image actually I pulled from my thesis, which is already like 8 years ago now. It's a long time. But in practical terms, what we're seeing is that if we're an observer on the bottom right-hand side of this image, the lens, that big circle, would be a galaxy cluster. And the source would be on the left-hand side is a faraway galaxy, which is behind the galaxy cluster. Then the light from that source will essentially appear like it's at that position in the top left-hand side, at the image position. And the amount of deflection is given by alpha hat, that little angle there. and it's equal to 4g, g is the gravitational constant, remember, times m, which is the mass of the lens, in our case, the galaxy cluster, divided by the speed of light squared times the distance to that from the center of the lens to the source. So what you can see there essentially is that the angle of deflection is directly proportional to the mass. So the more mass there is, the more deflection there is, okay? So that's something to bear in mind. Now, Christian, do you want to start the last poll?
Sure. I think what's interesting about the formula you're just showing is if you look at it, you have the gravitational constant, of course, which is tiny, and then you got c squared in the denominator. So it shows the deflection angle is really small unless you have a very huge mass, right? You really need a lot of mass.
You're giving away all my talk.
Oh, sorry, am I? Okay.
But yeah, very intuitive for you to think of that.
By the way, your animations are absolutely outstanding. So I see a lot of comments in the, in the best we've ever seen. Really
Yay.
amazing, amazing, really.
Awesome.
Okay, we'll wait a few more seconds and then we'll share that. Okay, there you are.
Oh, awesome. Awesome. Most of you got it right, actually. So gravitational lensing happens to anything, right, that passes through like this curvature. So as a galaxy in the very early universe, its light travels towards us, it will go through this curvature of the universe and it will be gravitationally lensed. And actually, like the best example that we have of lensing from the very early universe is actually the CMB, so the relic radiation from the Big Bang. That is gravitationally lensed by all of the galaxies and foreground dark matter and matter in our universe. And that takes us back like over 13 billion years ago. So very well done. Okay, so this is a simulation of gravitational lensing by a galaxy cluster. And what you can see here is these giant arcs. And these arcs are what we call strong gravitational lensing. And you can get a similar effect of this, like when you move like the stem of a wine glass through like some light source, you can see like very similar effects. And that's how I like to show it when I try to show people how gravitational lensing works. And it really depends on where your light source is with respect to that center mass, right? In reality, we do see these things actually. If your galaxy is perfectly behind your lens, in this case, the lens is a single galaxy, and you've got a faraway galaxy behind it, you can get an entire ring because the light gets distorted into a perfect ring shape. This is what we call Einstein rings. You can also get some really pretty visuals from this. This is the Cheshire Cat Galaxy Cluster. So this is a galaxy cluster, and you can see all this distortion, which is made essentially like a smiley face. So I love this galaxy cluster. There's also one that's like a space invader. I love that one too. Strong lensing doesn't just cause arcs, but in some cases, you can also get multiple imaging. So you can get duplicates of the same galaxy. So this is another galaxy cluster called MAX J1149 plus 22223. It's a frontier fields cluster. So these were heavily like observed by the Hubble Space Telescope. And so there's some scientists, and they saw this galaxy in 2014. But in particular, what they noticed was that there was a supernova going off in this galaxy. So a star exploded in this galaxy. And then this is really interesting because this is a multiply lensed galaxy. So there was more. So they went back into the archives and they found that that same galaxy, you could see the supernova go off in 1995 in that top left-hand galaxy, which is like the exact same galaxy as you're seeing in all the pointed objects. And then the supernova goes off in the middle galaxy in 1964. And what's really cool about this is called time delays. So because the light travels in different paths, right? You can expect that some will get to us quicker than the ones that are distorted the most, right? Because the ones that are really curved, it will take longer. The ones that are curved a little bit will get to us quicker. So what's really cool is there is a fourth lensed galaxy of that same object in this image. And they were able to predict that the supernova would go off in that next galaxy in 2015 on a particular day. And they looked for it and they found it. Indeed, it went off. This is supernova Restal. And from it, you can calculate the expansion of the universe, which is pretty cool, I think. Me personally, I work on weak gravitational lensing. So this is another galaxy cluster, and you probably can't see any gravitational lensing here at all. So weak lensing is a little bit more tricky than strong lensing because you can't see it with your naked eyes. And how it works is that if you've got some perfectly circular galaxies and your gravitational lens moves in front of it, so this is your galaxy cluster or your big dark matter halo, you'll see that the galaxies get their shapes become elliptical and they're orientated in like a kind of tangential formation around the center of this mass, right? So it kind of becomes similar to those arcs, but less circular, like just kind of stretched a bit in those kind of orientations. And so essentially what I do is I measure the ellipticities of galaxies. And so the ellipticity of a galaxy is defined from its semi-minor and semi-major axes, A and B, and the angle orientation of this ellipticity. I've given you the formula for it down there. But there's essentially like two components, an E1 and E2. They're not so important, I guess. But in order to figure out where dark matter is, we need not only the ellipticity of a galaxy, but the ellipticity with respect to the center of mass, with respect to some reference point. So in our case, the center would be a galaxy cluster. And we want to know the tangential ellipticity, because that's the effect that we would get if there is gravitational lensing. And so the tangential ellipticity, E plus, I've shown there, you can see the values for each of them. So if the galaxy is like directly above and perpendicular essentially to the center of the galaxy cluster, then it would have a high tangential ellipticity. But if it was like this, then it would not have a high tangential ellipticity. There's also a cross ellipticity. That's not very important. But this is what we call gravitational shear. Okay. And shear is what we're interested in, not the ellipticities themselves. And the reason being is that galaxies are already intrinsically elliptical, right? So they're not perfect circles. But thankfully, because galaxies are randomly distributed, you would expect that you would get all orientations of galaxies, and these would cancel each other out if there was no mass there, because there would be no shear. So the idea is that with weak lensing, we can take an average of many galaxies, and then we can figure out if there's an excess of this ellipticity direction, and that will tell us if there is mass there and if there is gravitational lensing happening. And so with weak lensing, you'll find the average shear is larger than 0 when you average out all the orientations of your elliptical galaxies. In practice, let's say we have a galaxy cluster at that blue point there on the left-hand diagram, and each of those lines could be shear values or ellipticity orientations. The stuff that I'm interested in is shear profiles, which is what is on the right-hand plot there. So it's showing tangential ellipticity on the y-axis against radial distance on the x-axis. And so you average over all of these points and you'll see a tiny little blip at the kind of front there. And that shows you like the tangential ellipticity like trails off as you go further and further away from the center. So you can see there already that it's an incredibly difficult thing to do. You have to average over thousands and thousands of galaxies even to get a good signal. But it makes it harder because, well, I said real galaxies are elliptical. The shear is tiny, and Christian mentioned that, he gave it away. The shear is typically changes the shape of the galaxy by less than 1%. And then you've got telescope blur when you're observing it through a telescope, and also like atmospheric conditions that you're seeing your galaxies from. So maybe you have like temperature fluctuations in the atmosphere, etc. That will blur your galaxy a bit. And then if you're imaging off a detector, you'll have pixelization effects. And then also you've got noise. So getting this 1% measurement of a shape of a galaxy is incredibly difficult. Okay. And that's why we want to do it from space. That's the Euclid Space Telescope that launched last year and just got its first images. And that's one of the main science cases that it's set out to do, is to map the dark universe essentially through gravitational lensing. And if you do it from space, then you get rid of all that this blurring effects from the atmosphere. Euclid is going to observe 15,000 square degrees of the sky, so everywhere except like the plane of our Milky Way essentially, because there's a lot of dust there and they would affect our measurements of the galaxies. And Euclid specifically is not just doing these measurements of weak lensing around galaxy clusters, but it's going to get the ellipticities to make an entire map of dark matter. And to do that, you essentially do the same measurements, but with respect to every single point on the sky. And this is something I've done before, and it's hard. It takes a lot of work. This is from the HERO survey. And on the left is the dark matter map that I made. This is just 44 square degrees of the sky. Euclid is doing 15,000 square degrees of the sky. The green circles there are galaxy clusters. So the larger the circle, the more massive a galaxy cluster is. And yeah, these measurements were really difficult to do. Limited galaxy shapes based on Earth-based, ground-based telescopes from the Hyper Supreme Cam in Japan. And we know those galaxy clusters are there because we have X-ray data, and you can see the X-ray data from ROSAT, a space telescope, on the right-hand side of the same region of the sky. Okay, so the X-rays are also important for allowing us to see dark matter in the universe and learn more about dark matter. So galaxy clusters, you can see from this train wreck galaxy cluster, is composed of X-ray gas, hot X-ray gas, gravitational lensing from dark matter, and then only 1% of galaxy clusters is in stars. But if we look at the entire contribution of the mass of a galaxy cluster in all X-rays, dark matter, and from the optical, in particular for colliding galaxy clusters, this is the Bullet galaxy cluster. So this galaxy cluster has collided and passed through one another. You can see that the stars, the optical, the galaxies, they've passed through, like the two clumps are separate. And you can see the blue, which is the dark matter, that's followed very closely with the galaxies and the stars. It's completely passed through. And this tells us that the dark matter is weakly interacting. It's not like collided, which is what we see with the pink, which is the hot gas. The hot gas has shocked. It's interacted with each other. The dark matter in blue has completely passed straight through. So another way that we can learn about dark matter through galaxy clusters and lensing and X-ray gas and galaxies is by measuring the distance between the components of the galaxies, the dark matter, and the baryonic gas. So depending on the particle cross-section of dark matter will decide how the separations between these three components lie. And that's another hot research topic of astronomers. And lastly, the reason that I am interested most in galaxy clusters is that the universe looks very different depending on the dark matter and dark energy we have in the universe. So on the left, you have a simulation of a universe with dark matter and dark energy. On the right, you have a simulation with dark matter only. And so you can see in a universe with dark matter only, you form more dense nodes, and galaxy clusters live in those nodes. They live in the densest regions of our universe. So you form bigger clusters essentially, and you form more clusters compared to if there's more dark energy. So kind of my research is looking at how many galaxy clusters are there in the universe, how much is their mass, can we use it to constrain dark matter and dark energy? And the exact amount and distribution of dark matter and dark energy is important because it determines the fate of the universe. And like, literally, I am not joking. So we know after the Big Bang, the universe went a rapid acceleration known as inflation. We're still accelerating today, but we still don't know what's going to happen in the future. And there are essentially like four main scenarios that could happen. And these all depend on the balance between dark matter and dark energy. Okay, so one possibility is that the universe just stops expanding and it just stays still. And that would be great. We'll just keep seeing the same night sky as we do. Another possibility is that if we have too much dark matter in the universe at one point might stop expanding and then go into a reversal. So it will start collapsing in on itself. And this is known as the Big Crunch. So some theories predict as well that there is a cycle of these kind of expansions and contractions where we would go shrink back down to a single point, to that single Big Bang point in our universe again. Maybe we'll keep expanding at this rate forever. The universe will get colder and colder as things get further and further away. This is known as the Big Chill. And then lastly, the universe might continue accelerating its expansion. And if it continues expanding and accelerated expanding, there could be a possibility that it expands so quickly that even the atoms in our bodies are like completely torn apart from each other. This is known as the Big Rip. And if we have too much dark energy in our universe, then this is likely the fate of us. We'll just be torn to pieces. And yeah, that's the reasons I've been interested in what I do. Hopefully you found it interesting, and I'm happy to take any questions.
Maggie, thank you so much. Would you just mind stop sharing so we can see you properly, and then we'll
Yes.
do that.
Yes.
That was absolutely magnificent. Really, thank you so much. The animations were outstanding. Your explanations are so clear. I think you probably have a lot of people who want to study this now because you make it look so easy, which is so difficult to do. Really fantastic. So before we'll go on, yeah, please put your questions in the Q&A. I see one there. So I'm sure you have a lot of questions. Please put it there. I just want to ask you two questions first. And the one is that's the burning question really. Do you think that we'll know maybe within the next 10 or 20 years what dark matter or maybe even dark energy is really about? Or do you think it's going to remain a mystery for a long time?
So you saw my particle accelerator plot.
Mhm.
We're chipping at that all the time. They're building bigger and bigger particle accelerators all the time and coming up with new ways to try and detect it. I think eventually we're going to run out of space. So if we don't like detect it, we might know that it's not what we think it is. But I can't say for sure in 20 years time. I think in 20 years time, we will know if it's definitely like a particle.
Okay, well, that's good.
We,
And the
we
other
might be
question,
able to rule it out. Yeah.
yeah, it's a burning question. By the way, I have to really say again, I put the link of Space Mog from Dr. Lieu or Maggie into the chat. So please go and have a look at her YouTube channel. She's just a
Amazing.
brilliant educator. It's such a difficult subject. The other question I wanted to ask you is more what you're doing in teaching because you do machine learning, which is AI. It's so exciting and astronomy. Can you maybe elaborate a little bit more to the audience what this is all about?
Yeah, so machine learning is about training algorithms to automatically identify patterns that perhaps humans can't see. And back in the early days, actually, people would manually have these giant plates to like detect, oh, that's a galaxy and circle them, etc., do its measurements on them. And even till recently, people have been picking out galaxy clusters by eye. They've been saying, oh, there's a big group of galaxies. That must be a galaxy cluster. Let's see if there's some hot gas there. Yep, it's definitely a galaxy cluster, like that. But like I said, Euclid is seeing like 15,000 square degrees of the sky just for our weak lensing measurements, we need thousands and thousands of galaxies to measure the ellipticities of. We need to detect these galaxies in the first place. One of like my first machine learning projects actually was to detect asteroids in Euclid data, in Euclid simulations. And the reason being is that asteroids move across the sky. So if you take an image of it, it will seem like it's an elliptical galaxy. And if we included those in our lensing measurements, they would completely mess it up because we think, oh, that's a
Right.
elliptical galaxy.
Yes, 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 of course, of course.
So we want to remove it. So using machine learning, I was able to quickly identify all of the asteroids with like, I think it's like 96% accuracy, and then
Right.
remove them so they don't interfere with our galaxy ellipticity measurements. Yeah.
That's a very good example. Thank you. Okay, so I'm going to go over to the audience questions now. So Richard Renner is asking, very good presentation. Couldn't we agree more with that? Thank you. Question. Do you think that the recent verification of gravitational waves helps us hinder research on dark matter and energy?
I'm not sure what you mean by hinder research. I think it will help us even like improve research actually, because even gravitational waves can be gravitationally lensed. And there are people who are working on that to determine like how they're changed. If there's time delays and things like that, we can do measurements of the expansion of the universe, like we did with the supernova multiple imaging. Yeah, I think it really does help rather than hinder.
Right, right. That's clear. And Richard's coming with another question. Do you think this is about the Hubble tension, actually? Do you encounter much debate about the constant of the Hubble constant? Yeah, currently is.
So there is a lot of debate about the Hubble constant. And there's been debates about the Hubble constant for a long time. I think the problem is that we have multiple different ways to measure the Hubble constant, from supernova to even galaxy clusters to CMB, and these all have their different uncertainties and biases and stuff. And if you don't correctly account for these, it can lead to discrepancies. And every astronomer, every scientist is trying to get smaller and smaller uncertainties on their measurements, but they might not be completely correct. Thing with supernova is that we don't actually have that many measurements. So we'll have like a handful of measurements, and we're saying, okay, the expansion of the universe is this based on, I don't know, 10 objects, right? So statistically, is that even significant? I think that's one of the reasons that you can't compare them very well. These different kind of, they call it like the cosmic ladder because it's like different distances, right? And yeah, the CMB is great, but it can also have, everything relies on models, and you need to correctly input all your biases and uncertainties and correctly carry those through. And I don't think we're there yet.
Okay, so it could still be uncertainty in statistics or just measurements and so on, right? That's what you're saying, right? So,
Yeah, even in mass measurements, actually. So I can tell you that clusters of galaxies, the masses, there are like three big like collaborations that did like a crossover study of 50 galaxy clusters. And all they had to do was, using weak gravitational lensing, they start off with the same data. They three groups, 50 galaxy clusters, they measure the masses, and all three of them got completely different results, and they like weren't within the uncertainties. I think one group was like 2 sigma out from each other, and then the other one was more than
really?
3 sigma out. Yeah. So you
Oh,
always have issues.
well, that's good to point out. Thank you. John is asking, how can lensing be used to identify specific masses of dark objects?
So in the example that I gave of galaxy clusters, we can measure how distorted these faraway galaxies are based on the center of galaxy cluster. And that tells us how much mass is there in total. And then we know how much light is in the starlight of the galaxies. And so we can calculate how much stellar mass there is, and we can subtract that off. And then with X-ray telescopes, we see the X-ray halos, and we can take off the mass from the gas, X-ray gas, and then what remains is unaccounted for. So we call that dark matter mass.
Okay, thank you. And Natalia is asking interesting questions actually about deconvolution. If the far away galaxy is distorted by gravitational lenses, is it possible to restore its original shape? So let's assume there's some alien outside in space looking at Andromeda, and it looks all strange for them. Could they actually restore the shape?
Yeah, absolutely. Especially in like the strong lensing and the multiple imaging cases, there are models to essentially simulate the entire system, including what the original source object looks like, to reproduce the images that we see.
Oh, yes, it's a clear
Yeah.
yes. Thank you. Okay, next question. Somraj, I hope I pronounce your name correctly. Would dark matter be present every time after the proceeding of the Big Bang till the end of the universe? Oops.
So I think we believe that it is. There's no reason for us not to believe that it would change. I don't know. Yeah, I think we believe that it's always been there. It may be changing, but that might be another theory. With our current theories, there is no like,
Okay. And
yeah.
Sikanda, nice to see you, Sikanda. What would happen to the theory of gravity if we do not find these particles? How would it be changed? That's a good question.
Well, already there are so many theoretical physicists working on new theories of gravity that would explain away dark matter altogether. And like a famous example is like Stephen Hawking.
Mhm.
He was working on a grand unified theory of everything to unify gravity on the large scales does not um, does not agree with quantum theory, quantum gravity. So everything on small scales does not work in the same way as the large scales. So if we can come up with a big theory that makes everything agree with each other, that would be wonderful. But we need another Einstein to do that.
Or maybe a few even, right? It's so complex. Okay, Natalia again. Why do we sometimes see Einstein rings and then an Einstein cross?
So an Einstein cross is like multiple images,
Mhm.
and they typically occur in a cross formation is how they're imaged. But it's completely geometrical, so it just depends on where the behind object is in respect to distance from the lens, essentially.
Right. Yes, so good answer. And Bob's asking a very interesting question here. Is it possible to replicate Edison's experiment during the next solar eclipse, which is coming up in April, of course?
I think so,
How much
yeah, definitely. Definitely, it would be worth doing. If anyone
would
wants to do that, you've got some telescopes at your disposal.
actually good point. Good point and good point,
I,
Bob. So
we've got a big solar eclipse coming up in the US. It will be visible in quite a large part of the US this year.
fine.
So, prime
And Canada
opportunity.
and Canada. Part of the East Coast, yes.
Not in
So
Europe, unfortunately.
no. But it's very exciting. I'm going all the way down to Houston, and it's a very exciting. Texas will be. Okay, Gerard, nice to see you. If you look at a specific galaxy, it looks elliptical just because of the angle you look at the galaxy. How is it possible to find out that not the angle of view, but gravitational lensing is causing this shift? That's a good one.
Yeah, I think that I tried to answer that in my talk. The idea is that there are so many ellipticities, but they're all orientated in different directions. So if there wasn't any gravitational lensing, if you averaged all the ellipticities, it would just average to zero because you've got one that points that way, one that points this way, and they're the same elliptical amount. But if there was lensing happening, it would change it a little bit. And if you take averages of loads of them, then you would get some signal, essentially.
Right. Yes, that makes complete sense. Okay, I'll just skip the next one. Let's see here. Oh, yes. Okay. I think it's okay. We got the question. Thank you. Andre is asking, do you know Thomas Herzog? I think that's, I'm not quite sure.
No, I don't think I know him.
Okay.
Sorry.
I'm not sure what you meant, but maybe Andre, you can tell us who that is. Okay, what is the smallest scale at which the effects of dark matter are detectable? Can the effects be detected within our solar system? Oh, good question. Hmm.
Hmm.
So if you
Well,
could only look at our solar system and had nothing else, would we actually know about it?
well, we hope that we can see dark matter in our solar system, right?
Mhm.
Um, like I said, there's 6 times more dark matter than there is visible matter. So there should be dark matter passing through us all the time. And that's the consensus of many like dark matter detectors. They're trying to find some small interactions of dark matter with anything else to trigger some kind of detector to say, oh, we've detected dark matter. So far, they haven't found anything. There is a theory actually that the extinction of the dinosaurs was due to dark matter.
Really?
Uh,
I've
yeah,
not heard
there
that
is.
one.
Have you not? Okay,
No.
so we're in a galaxy, right? So our solar system's in a galaxy. And actually we move up and down through the plane of the galaxy as
Mhm.
we travel. So at some point, I can't remember how many years a cycle is, but at some point we go through the densest part of the disk of our galaxy where there's most dark matter. And there's a theory that because there's so much dark matter there, we attract more asteroids and other meteorites and stuff, and that is what led to the bombardment of the start of the Ice Age, etc., that wiped out the dinosaurs.
That sounds, sorry, intuitively, I would say that sounds rather far-fetched. I may be completely wrong. I'm just saying because when you had the formation of the dinosaurs, you had a lot more asteroids then. So you're basically saying that the cause of that may be that we're moving through a dense part of dark matter. Wow, I would be surprised, but who knows?
There's a very popular book. I can't remember. Kate Freeze, I think her name is.
Okay.
I
Interesting.
and she's a very good theoretical physicist and wrote
Very
about that.
inspiring. It's always good to learn. Thank you. I did not know that. Okay, next one. Hans Helmut is saying, can Einstein's cosmological constant lambda describe the influence of dark matter? Uh-huh.
So lambda
Sorry.
lambda is more about dark energy, actually. So when Einstein originally introduced his lambda term into his relativity equations, it was because he thought that the universe was static. And so his equations made the universe expand. So in order to correct for it, he introduced the term lambda to say, this will fix everything. But later, when we realized that the universe was expanding, he said that like having lambda was his biggest removing lambda, sorry, was his biggest mistake. No,
Yes.
including lambda was his biggest mistake, sorry. And now recently we've added back lambda to explain some of the expansion of the universe.
And Gerhard is saying, again, thank you for excellent answers and great presentation. We'll take one or two more questions. Thank you so much again. I completely agree. Michael's saying, did dark matter, oh, here we go, philosophical. Did dark matter exist before the Big Bang? This is getting very difficult now.
So assuming that there is a big, before the Big Bang, and there are actually people who are working on theories that predate the Big Bang. I don't work on that, so I can't comment on it really. But yeah, there are people who work on pre-Big Bang theories.
That's incredible. That's incredible. Okay, and final question here. Since the Hubble from Somage again, sorry if I mispronounce your name. Since the Hubble telescope in space, so is there a prediction to get dark matter or found it would be over our limits? Wait a minute. Sorry, I don't get it. Maybe you get it, Maggie. I'm not sure I understand this. Since the Hubble telescope is in space. Oh, I see. Is there a prediction to get dark matter or find it or find would be over? I'm not quite sure I understand the question here.
I'm not sure what the question is either, but many of these lensing experiments, well, to measure the accurate shapes of galaxies is using Hubble, especially the strong lensing cases. All the MAC clusters, frontier field clusters I've shown, those were Hubble images where you can very distinctly see the arcs, etc. So Hubble is doing a lot for us.
It is. And Glenn, finally, thank you very much for putting a link for the extinction of the dinosaurs. Maybe we'll give a talk one day about this because this is very interesting. I certainly did not know that. I'm just going to go very quickly through the webinar chat and read out the last one because I think it's very appropriate. There's Dr. Lieu. Thank you for the excellent talk. This is by Brian. Incredible to uncover the details of dark matter. This has increased my interest in the topic, Brian. And this goes for everybody else. Thank you so much. Thank you, everyone, for attending. This has been a most incredible webinar. Thanks again, Maggie, for this really beautiful talk. I can't find enough superlatives to praise your really excellent presentation. Thanks, everyone, and we'll see you soon again. And have a wonderful weekend. Thank you.
Thank you.